Hello everyone and good morning. So thank you for introducing us. I'll directly dive into the presentation. So it's very clear to this community for sure that the landscape of web tracking has changed over time. We went from traditionally the cookies that are being used, flash cookies that get used, towards more different types of tracking as of today. Industry has moved to more surreptitious form of tracking, something like ever cookies and canvas fingerprinting. Um, so the question remains, today can we be confident of all the tracking information about our systems that is floating around on web? Is there any way of getting a holistic picture of this? And this is exactly the problem we are trying to tackle. We want to devise a technique which is irrespective of the tracking mechanism used and which can look at the network traces and identify tracking information here. To strengthen a point a little bit further, why is this tracking information useful? Well, it's not just a threat from a privacy threat from the industry or the domains we share this information with, but there could also be adversaries who have the capability of tapping onto large network traces at different vantage points. In fact, we know that NSA has been known to do this. Okay. So before diving into what we do and how we do it, I want to define trackers from our perspective. So note that all of this is from a network vantage point. The definition of trackers for us is any piece of string that can uniquely and persistently define you as a user or a device. By uniqueness, it means that no other system should have the same string, and by persistent, it means that the string should exist for more than certain minimum period of time. For simplicity in this project, we consider device and user very similarly, and this is an assumption clearly because one human can be using multiple devices. Moving on, so a little bit more about our data. We used 15 days worth of network traces collected at the border of an enterprise network. We have about 512 IP addresses with 4 NATs in this network, amounting to about 3.5 terabytes of data. That is huge amount of data to look at. In order to parse out what these NATs contain behind them and to see the number of different machines, we use the DHCP and NAT logs to find out individual MAC addresses and thereby individual devices sitting behind them. This is an overview of what the data looks like. The task is now, given this huge size of data, find out individual trackers that are floating around. The key challenge, if you simply want to apply the conditions of uniqueness and persistence, is pretty straightforward. You have a list of strings and you want to find the strings that are unique and persistent across these lists. However, when trying to do this at the scale of 3.5 terabytes, it is difficult. One, because of the scale. Apart from the fact that it's huge, consider what is the unit of string that you're going to think about for validation as a tracker. Would it be all the potential substrings of your network traces? If that's the case, you're automatically changing your problem statement to a quadratic one, and quadratic of 3.5 terabytes again is huge. The second is the problem of false positives in this case, marking strings that are not as trackers as trackers. The false positives, I'll give an example of why this is important and is a big problem here. So Mobin, my friend, she has a favorite song she likes to listen to, and let's say no one else in the network listens to that song. If we look at a network trace of just those 15 days, this entire byte stream of the song will work as an identifier for her. And this is a false positive because this is due to the limitation of the data size and not because the definition was wrong. So this is a big problem and this big concern with this problem, and we need to deal with it. So these are the two main challenges we're facing. And what are some of the ideas that we're using to work around them? The first one is we use multi-stage filtering. So we progressively apply filters one by one on the raw traces and work on the final set of strings that's left. These filters are chosen such that they reduce the false positives by a maximum amount while constraining the number of interesting strings we could potentially be losing. The second one is sliding windows. So as I said, what would we consider as a unit of tracker in these raw traces? So instead of considering all possible substrings, we use sliding windows of fixed length. And later we work with these sliding windows all throughout, and at the end we build the context back from which it came and to do further analysis. The third one is streaming algorithms. We stress quite a bit on using just streaming based algorithms and not ones that need data in the memory because of the size of the data. if it was not for, if you were to use anything apart from stream algorithms, this might not work. So going over the architecture, this is a schema of the solution that we're proposing. Again, to reiterate the problem, we have rod network traces at the input, and we want trackers or identifying information at the very end. The first step that we perform is pre-processing using Bro, which is a network analysis tool. Out of this step, we get clear connection and payload information in a clear format to work with in the next step. The next step is multi-stage filtering. This is the one I was talking about, where we apply filters progressively. We have two main types of filters. The first based purely on connections. So connection here is defined simply by the source port, source IP, destination port, and destination IP. So based on these, we apply three different filters. One, we remove all the encrypted traffic. This is because validation of encrypted traffic as trackers is difficult. And second, they cause a lot of false positives. The second is we remove any server side, any byte stream coming from the server. This is because the idea is if a string has to be used as a tracker, it needs to be sent by both the client and the server. And since the server data is orders of magnitude bigger than the client-side data, we chose to just keep the client-side data. And third one, finally, is server specific to certain users in the network. So consider this. You have a network with 710 users. One of the user makes a connection with a domain which no other person in that network makes a connection to. Pretty much anything that will come from that domain might look as a tracker for this user. And since it contains URL paths and all of those that will show up as false positives, we plan to remove all of them. And we hope that it does not really compromise on the tracking information we're trying to capture. So post this step, we have filtered connections that we work with. To move forward to apply the next set of filters, which are based on the string values, we need to slice these connection raw traces into sliding windows that we spoke about. So this is the slicing step that is shown in the diagram. Once we have that, we apply our definitions of uniqueness and persistence. So this is where we use two streaming algorithms to apply these conditions. And once we're done with these two set of filters, we are left with the first set of potential trackers, potential strings that could be used as trackers. Note, however, that until now, we still have sliding windows. So these are strings of fixed length, which when you look at it, might be difficult to validate whether these are trackers or not. So to go forward from here, we use these sliding windows to build back the context they came from. So for example, if it's cookie information or URL path, we build back that was a cookie or a URL path. And in order to do that, we maintain some metadata along with each sliding window while throughout this process in order to build this context. Once we have the context, we then move over to the next step of manual analysis, which Mobin will now cover. Moving on to her.
Great, thank you. So to recap, we started with 3.5 terabytes of data, and the idea was we're going to build a data processing pipeline and boil this data down to a set of candidate identifiers that an analyst will look at them to find potentially new and interesting identifiers. So what does after processing through the data pipeline, what is the data reduction we got? 0.1%, so we were able to reduce the data down to 0.1%. But when we looked at it in terms of, okay, what does this mean for an analyst? There were like 6 million candidate identifiers. So there is no way that an analyst can look at these manually and investigate what are new interesting potential identifiers. So at this point, it was clear to us that we need to go further than what data processing pipeline Sakshi discussed. We need to add more filters. And how do we go about doing that? So if you recall, so far, we have not talked about any application layer information that we have used to filter out any of the strings. So what we're going to do now is add that information since we reconstructed the context in which the identifiers are occurring. So the first thing we looked at was, okay, what are the major context categories in which these identifiers are occurring? So this slide shows you the distribution of the context categories. And you can see that cookie is one of the most dominant categories. So 50% of the identifiers appear in cookies, which is great because it reaffirms that, okay, these are with the high likelihood true positives. But these are also uninteresting for our purposes because we're looking for potentially new identifiers that are unknown to the community. So the first filter that we add here is we're going to remove the cookies. We're not going to analyze these further. The second filter that we added was to remove any identifier that appears in URL paths. So the reason for this is basically they comprise about 13% of the data, and we found just based on a preliminary analysis that these had a very high false positive rate. So again, we're keeping a balance of finding new interesting identifiers versus actually reducing the false positive rates. Okay. The next thing that we looked at was what is the temporal persistence of these reconstructed identifiers. So recall that we although had previously added a persistence filter, the reconstructed identifiers do not necessarily retain that property. And indeed, if you look at this distribution, it is the case that a lot of identifiers lose their persistence property once they are reconstructed. So the third filter that we add here is to remove anything that does not persist over days. Okay, to recap, we have now 3 filters that we talked about. They were based on the context and the reconstructed identifiers. And using these 3 filters, we were able to reduce the data further by 85%. And now we're left with 12,000 identifiers that we needed to investigate manually. So I'm going to just briefly give you the highlights of what we found using our methodology. More details are in the paper, and I encourage you to go and read the paper for more details. But broadly, we divided our results into HTTP identifiers and non-HTTP identifiers. In terms of HTTP identifiers, first, our work reaffirmed the existing knowledge that mobile device identifiers such as IMEI numbers, phone make and model, advertising ID, they are conveyed in the clear by various mobile apps. But what is less understudied is what if you consider a desktop-based environment, besides browsers being conveying tracking information, what other softwares or applications are conveying information, tracking information to the servers around the world? And what our work found in this category was Skype and Dropbox. They send out identifiers in clear. And what is very interesting about Dropbox is that it sends out an identifier every single minute without even requiring any user action. Okay, we also found non-HTTP identifiers. I'm just going to highlight 2 here. The first one is your instant messenger apps. They basically send out nicknames out in the clear in ping messages. So MSN, IRC, we found those to be sending out information. We also found, secondly, device identifiers being sent out by Apple's push notification service. The details are in the paper, but what I want to highlight here is that this is a unique device identifier that Apple constantly sends around. The Apple push notification sends around to Apple servers around the world. And using this identifier, we were able to identify 68 different Apple devices in the data set that we had. Okay, to conclude, we presented a methodology here to mine large-scale network traffic to find potentially new and interesting identifiers. And this is really the core contribution of our work as the methodology. How do you design a methodology that will scale up to terabytes of data while you're managing the false positive rates that you need to analyze? Our code is publicly available. You can check out our GitHub repo for that. And using the methodology that we developed, we reaffirmed some of the existing findings of the literature that exists on trackers. And we also found new instances of trackers that were previously unknown to the community. So with that, we'll take questions. Thank you.